Okay, so let's get started. I'm going to finish up the section for thermochemistry. This is about what is called the Hess Law and Hess Law. And this is something about actually bookkeeping the heat of reaction and how we can understand their temperature dependence and so on. And this is for the last time that I think that you get familiar with what is called the standard enthalpy changes. Okay, so this is what do you mean by standard is we need to tabulate the thermodynamic variable, and there's something table in the end of the book. It's called the thermodynamic data, and a lot of data are showing up. And the most important one is what is called we call standard state. Standard state has a symbol of this. Okay, that means that you are at 1 bar pressure. Okay, and this one comes in specified temperature. So the temperature has to be specified for define the standard state. And typically they like to use temperature 298 Kelvin. And I want to draw your attention that if you look at the back of the table book, there's a table 2C7, and title is Thermodynamic Data. And then if you look at that, actually they said at 298 Kelvin. So we cannot really provide all different temperatures and provide thermodynamic data. And this table actually gives you this, what is called the thermodynamic data. And the example of thermodynamic data is heat of formation, enthalpy, and also Gibbs free energy of formation at the standard state, and also what is called the CPM at standard state at 1 bar pressure. And these are all given for different elements and compounds. So these are the one that was given here for us to understand. And so for us to understand the Hess law is for you to figure out, let's say, delta H reaction. So I want to know what is the heat of reaction by looking at the table from here. So this is coming from actually calculating, you're looking at the table at heat of enthalpy of formation. And because of the limitation of this data, typically this one you are saying, okay, you can do that at 298 Kelvin at room temperature. Certainly this one means a 1 bar pressure. Okay? So this one we will show you how to do. And this one is essentially, what about heat of reaction, temperature 1 versus heat of reaction at temperature 2. So temperature dependence of heat of reaction and how we're going to handle that. So at different temperatures, right? So we know some reference temperatures, and then when you change the temperature from one temperature to the other, because reaction sometimes you heat it up at a high temperature. So those are the two things that we need to cover, and that's just a simply matter of the bookkeeping. Okay, so the standard state is 1 bar, and so let me show you an example. So this is an example of, they put it this way. So this is the notation. Sometimes the people actually put it this way. Okay. So this is the same notation. I think the author, Dr. Atkins, going to decide to put it in. The process for a company for changing it is going to be like this. So this is a vaporization enthalpy at 1 bar pressure, and you say, what about temperature? And you have to ask whether then the information has to be specified to get the answer for that. Okay? So this one is certainly as an example of somebody should write in this way, 298 Kelvin. Okay? So then this one is a complete description, and you can find out. And 2 is now that I'm going to talk about this one. This is very important. So this is about the formation, right? An enthalpy of formation at 1 bar. That's what that is. And then there is a very important consequences. Everyone need a reference point. The fact that this one we have this height. This is not from the sea level, but we need a reference point. Then from this position is so much height from your reference point, and they want to give out the reference point on this. And for E0, and this is something that you probably remember your freshman chemistry for pure elements. At this condition, right? And also, if somebody says, typically they imply it to at room temperature. This is a sort of has to be given, but if I look at the table, there is already temperature has been specified, and it has to be done this way. So, what are the examples of pure elements? Hydrogen. At normal ambient pressure and temperature, is it a gas? Right? So this is an example of pure elements. What about H2O? I mean, it can be, I think that this is a typical ambient conditions of liquid, but this is not pure, right? So therefore, if I bring this notation of, okay, this is the one, I want to know delta H of formation in the standard state for this pure element that is in the gas state is 0. Okay? Whereas this one is not. It's not 0. And another example, enthalpy, but now hydrogen, I'm going to put liquid. This one is non-zero. Right? So those are the two things that you have to consider. Is it pure? Yes. And is it the right state at this one bar condition and one temperature that they designate, which is room temperature. So this is only if you have a pure element. And anything else is not. And you don't have to worry about it. They are given in the table. Look at once again this massive table, table 2C7 in this textbook. They give out all the thermodynamic data, heat of formation on different compound elements, and then in different physical state. Okay, so then you can find it out. So what is a Hess law? Is essentially I want to know reaction, heat of reaction. Right? This is a heat of reaction at standard state, and for that I want to say heat of reaction is, we talk about your product, heat of formation multiply by your constant mu minus mu times heat of formation at your reactor. It's almost like your final, quote unquote, final versus your initial. And that's going to change. Okay? And then I love to show you this example where you have 2H N3. Maybe I should delete this and then I can say. So this is a Hess law, and this equation should make sense for you when I actually deal with a real example shown here.
What is the symbol next in between the delta and sigma?
Yeah, so that's one is what I'm going to show you to you. It is essentially defined by reaction. Okay? So this is something that you put it in, and I will show you that how that mu, what's the meaning of the P. Okay?
No, but what's like the actual Greek letter shape so I know which one to draw?
The mu.
Mu?
Mu, yeah. So I don't know how to write. I write this way. You guys write that way. It doesn't matter which way you write. But it is something like a little bit skewed. It's not V. It is this way. That's essentially a constant defined by the reaction. So let me write as if you have a 2 NH3. What is this? NH3? That's ammonia, right? Ammonia react with nitroxide gas, and then you will generate H2O2, which is a liquid, plus 4 times N2 gas. So let's talk about this reaction. Right? This is a reaction. So it involves with generating hydrogen peroxide, nitrogen, when you react ammonia and this, I guess, of this poison gas of nitroxide gas. Do that, you get something useful out of it. The expenses of just something like pollution gas. So for this, so this is what I mean by mu. That's a constant. And this is, I guess, is a 1, and this is a 4. So I just simply do this, okay, if this is a reaction, heat of enthalpy, this is something that you want to know. And you don't have to actually do the experiment by simply looking at this table in the textbook, saying, okay, so the product, which is this, so delta formation, H, and I'll write H2O2 and the liquid, the standard state. Okay. Plus 4 times delta F N2. Okay, that's a product. Minus 2 times heat of formation. NH3. Okay. That's 2 times heat of formation. And all. Okay. So it's just a simple bookkeeping of what you do. But I just write it, and then immediately you look for something called pure elements, right? There's pure elements. Do I have anything pure elements here? And this is a pure element, right? And this is not. This is a compound. So you have to actually look up the table to figure out. And okay, this is a pure element. That's good. Is a nitrogen is a gas in their physical state at ambient pressure, right? It's not liquid, it's not solid. So therefore, this one, by definition, is zero. Okay. worry about that. And then I have to look for the tables, and then you guys have to look at, okay, so this is a enthalpy of formation was a minus 187 kilojoule per mole. You can find that in the textbook. And the minus, and this one is 2 times 64, 2 times 90. Okay, and then I finally get the answer called 1896 kilojoule per mole. And I want to emphasize the per mole unit that was to define this. That it has something to do with a reaction. Yeah.
Is the equation balanced correctly? So it looks like there's 6 H's on the reactant side.
See, 6 H's. This is a. I think I got something. Yeah. This, let me see. This is a 2. I wrote it down from the textbook. The textbook is full of like. Oh yeah. No. This is a. This is a. How many nitrogen we are talking about here is a 6. 8. Nitrogen number matches. Hydrogen number.
Nitrogen doesn't match.
Yeah, but nitrogen is
4
half.
and there's 8.
Oxygen.
On the one on the right, I would say make it a 2.
There's something wrong here.
Wait, nitrogen doesn't match either.
That way.
Yeah.
And then nitrogen.
Oxygen matches. We've got all oxygen.
Got one element out of the 3.
Yeah.
We'll think about that. I don't know. Let me have a look at the textbook and see what it says.
3.
So nitrogen, good, right?
260 something.
Oxygen, you got 2.
Doesn't matter.
2. Hydrogen, you got
Doesn't matter.
2. You got 5.
Oh my
So
god.
something wrong with the hydrogen. Okay. And
We balance the equation perfectly.
let's say, I just say this is a compound. Let's say that this is a compound A, compound B, compound C, and then this is nitrogen.